Imagine a world where whispers of the past linger in the present. A place where every shadow holds a story, and every corner is a portal to another time. Where echoes of forgotten conversations dance on the edge of perception, creating a symphony of memories that never fade. This is not the realm of fantasy, but the tantalizing possibility offered by time travel. A concept that has intrigued and mystified humanity for centuries. The very notion sends shivers down our spines, a testament to humanity's enduring fascination with the unknown. The idea that we could step outside the linear progression of time and experience moments long past or yet to come. We are temporal creatures, bound to the relentless march of time. Each tick of the clock a reminder of our fleeting existence. Yet, the human spirit yearns to break free, to explore the uncharted territories of the past and future. We dream of revisiting moments of joy, correcting past mistakes, or catching a glimpse of what lies ahead. Time, the relentless sculptor of our lives, dictates our every moment. It shapes our experiences, our memories, and our destinies. From the first breath to the last, we are swept along by its current. Each stage of life a chapter in the grand narrative of time. But what if we could control that current? What if we could pause, rewind, or fast forward through the moments of our lives? What if we could navigate the river of time, choosing our own destinations? The possibilities are as endless as time itself. The science of time travel, once relegated to the realm of science fiction, offers a tantalizing glimpse into this possibility. Researchers and scientists are delving into the mysteries of time, seeking to unlock its secrets. The quest to understand time travel is a journey into the heart of the cosmos. It challenges our understanding of physics, reality, and the very nature of existence. It is a quest driven by our deepest fears and wildest dreams, a testament to our insatiable curiosity about the universe and our place within it. We seek to understand not just time, but our own role within its vast expanse. As we delve into the mysteries of time, we are forced to confront fundamental questions about our existence, the nature of reality, and the very fabric of the universe. What is time? Is it a constant, or can it be bent and manipulated? This exploration will take us to the very edge of scientific understanding, where the known universe blurs with the infinite possibilities of the unknown. It is a journey that requires us to rethink everything we know about the world and our place in it. It is a journey fraught with paradox and uncertainty, but one that promises to illuminate the most fundamental aspects of our existence. As we stand at the crossroads of time, we must decide whether to embrace the unknown or remain bound by the ticking clock of existence. To grasp the complexities of time travel, we must first shed our everyday perception of time. Our daily lives are governed by the ticking of the clock, the rising and setting of the sun, and the changing of the seasons. We are so accustomed to this rhythm that we rarely question its nature. We tend to think of time as linear, an arrow flying in a straight line from the past, through the present, and into the future. This linear perspective is deeply ingrained in our consciousness, shaping how we plan, remember, and anticipate. But what if this perception is merely a product of our limited human experience? What if our senses and cognitive frameworks are not equipped to fully grasp the true nature of time? What if time, as we know it, is but one facet of a much grander, more intricate reality? A reality that transcends our everyday experiences and challenges our fundamental understanding of existence. Physicists have long proposed that time is not an independent entity but rather an integral part of the very fabric of the universe. This idea suggests that time and space are not separate dimensions but are interwoven into a single continuum known as space-time. Just as height, width, and depth define our three-dimensional world, time adds another layer, a fourth dimension to this cosmic tapestry. This fourth dimension is not just an abstract concept but a tangible aspect of our universe that influences everything from the motion of planets to the flow of energy. Imagine a vast cosmic sheet. This sheet is not just a metaphor but a representation of the interconnectedness of space and time. This sheet represents the fabric of space-time, a unified entity where space and time are inextricably intertwined. The curvature of this fabric is influenced by the presence of mass and energy, bending and warping in response to the objects within it. Every event, every moment that has ever occurred or ever will occur, exists as a point on this fabric. These points are not isolated but are part of a continuous, dynamic web of interactions. The past, present, and future are not separate entities but rather coexisting threads woven into the grand tapestry of space-time. This interconnectedness means that each moment is linked to every other moment, creating a seamless flow of existence. This concept, first proposed by Hermann Minkowski in the early 20th century, revolutionized our understanding of the universe. Minkowski's insights provided a new framework for thinking about time and space, one that would pave the way for future discoveries. It laid the groundwork for Einstein's groundbreaking theories of relativity, which would forever alter our perception of time and its relationship to space. Einstein's equations showed that time is not a constant but can stretch and contract depending on the speed and gravity of the observer. The implications of this interconnectedness are profound. They challenge our conventional notions of cause and effect, suggesting that the future can influence the past just as much as the past influences the future. If time is not linear, if the past, present, and future exist simultaneously on this cosmic sheet, then the possibility of traversing time takes on a whole new meaning. It opens up the tantalizing prospect of time travel, where one could potentially move between different points in time as easily as we move through space. It suggests that the past is not gone, the future is not yet to be, but rather, all moments coexist in a vast, interconnected now. This realization invites us to rethink our place in the universe and our relationship with time itself, offering a glimpse into a reality far more wondrous and complex than we ever imagined. Albert Einstein, a name synonymous with genius, revolutionized our understanding of the cosmos. His contributions to science are immeasurable, and his theories continue to influence modern physics. His theories of relativity, both special and general, unveiled a universe stranger and more wondrous than we could have imagined. These theories challenged the very foundations of classical physics and opened up new realms of scientific inquiry. At the heart of these theories lies the concept of space-time and its intimate relationship with gravity. Space-time is a four-dimensional continuum that fuses the three dimensions of space with the dimension of time into a single interwoven fabric. Einstein's special theory of relativity, published in 1905, postulates that the laws of physics are constant for all observers in uniform motion. This theory introduced the revolutionary idea that the speed of light is the same for all observers, regardless of their relative motion. This may seem straightforward, but its implications are profound. It means that measurements of time and space are not absolute, but depend on the observer's state of motion. It means that time is not absolute, as previously believed, but rather relative. This concept, known as time dilation, suggests that time can stretch or contract depending on the relative velocity of the observer. The rate at which time flows depends on the observer's relative motion. For instance, a person traveling at a high speed will experience time more slowly compared to someone who is stationary. The faster you travel through space, the slower time moves for you relative to someone who is stationary. This effect becomes more pronounced as you approach the speed of light. This phenomenon, known as time dilation, has been experimentally verified countless times, confirming that time is not the rigid, unchanging entity we once thought it to be. Experiments with atomic clocks on fast-moving aircraft and satellites have consistently demonstrated this effect. Einstein's general theory of relativity, published a decade later, takes this concept even further. It extends the principles of special relativity to include acceleration and gravity. It describes gravity not as a force but as a curvature in the fabric of space-time. This curvature is caused by the presence of mass and energy, which distort space-time around them. Massive objects like stars and planets warp the space-time around them, much like a bowling ball placed on a trampoline stretches the fabric beneath it. This warping creates what we perceive as gravitational attraction. This warping of space-time affects the motion of objects around these massive bodies, causing them to move in curved paths. Planets orbiting the Sun, for example, follow these curved paths due to the Sun's gravitational influence. This is what we perceive as gravity. The familiar force that causes an apple to fall from a tree is actually the result of space-time curvature. Time, being an integral part of space-time, is also affected by this curvature. The presence of a massive object can slow down the passage of time in its vicinity. The stronger the gravitational pull, the slower time flows. This effect is most extreme near massive objects like black holes, where time can slow down to a near standstill. Time dilation, a consequence of Einstein's theories of relativity, offers a tantalizing glimpse into the possibility of time travel, albeit in a limited sense. It suggests that traveling into the future is not merely a figment of science fiction, but a phenomenon rooted in the very laws of physics. Imagine two synchronized clocks, one remaining on Earth and the other embarking on a journey aboard a high-speed spaceship. As the spaceship approaches the speed of light, time dilation comes into play. Time on the spaceship slows down relative to time on Earth. The faster the spaceship travels, the more pronounced the effect. If the spaceship were to achieve a significant fraction of the speed of light, years could pass on Earth while only days or even hours pass for the travelers aboard the spaceship. Upon their return to Earth, the astronauts would have effectively traveled into the future. While this form of time travel is theoretically possible, the technological challenges are immense. Achieving speeds close to the speed of light requires unimaginable amounts of energy, far beyond our current capabilities. Moreover, the effects of time dilation become significant only at extremely high speeds, making this form of time travel impractical for all but the most advanced civilizations. Nevertheless, time dilation serves as a powerful testament to the malleable nature of time. It demonstrates that time is not the absolute, unchanging entity we once believed it to be, but rather a fluid dimension subject to the laws of physics and the whims of gravity.